Right now, you are sitting in the middle of a massive, invisible ocean. Every second, an immense amount of energy washes past you, completely wasted. Noise generated by modern infrastructure. For decades, engineers have tried to harvest this ambient soup, but capturing it has always required bulky antennas, rectifiers, and complex circuitry that are too large and rigid to fit into the smallest, most useful electronics. Instead, we rely on chemical batteries. Looking at this standard lithium-ion cell, you can see the explicit technical trade-offs: strict voltage limits, a finite number of charge cycles, and stark warnings against physical damage. But an international research team from the Queensland University of Technology and Nanyang Technological University recently began investigating an advanced class of quantum compounds known as topological materials. Curious, leaning in, while observing the internal structure of one specific crystal compound, they noticed a stark anomaly. The material was spontaneously taking in random alternating electrical signals from its environment and converting them straight into direct, usable electrical current. By proving that ambient environmental noise can be converted into a steady flow of current, this discovery provides a model for sensors and chips that could operate entirely on the signals already present in their environment. This behavior is driven by a quantum phenomenon known as the Nonlinear Hall Effect. Look at this diagram. Chaotic signals enter the material. Without diodes, a direct current flows out at a perpendicular angle. Most quantum effects require ultra-cold labs. But watch the thermometer here. As the environment warms to room temperature, that direct current stays unbroken. Normally, reliable performance from a silicon chip requires an absolutely symmetrical atomic structure. But when researchers looked closely at where the energy conversion was actually occurring inside this topological crystal, they found the exact opposite. The power generation is being driven almost entirely by microscopic flaws. Tiny gaps and missing atoms scattered randomly throughout the lattice act as the central engines for the quantum effect. For decades, engineers have spent billions of dollars trying to eliminate every possible imperfection from our microchips. Now, those exact structural flaws are the mechanisms enabling the material to harvest power without any traditional electronic components. Here is how it works mechanically on a microscopic level. At cool, lower temperatures, those missing gaps operate like tiny funnels, catching the chaotic incoming signals and forcing them into a focused stream of energy. But the scientists needed to know what would happen to that steady stream of energy if the material was exposed to significant changes in environmental heat. As temperatures rise, atoms vibrate, generating intense kinetic energy. These vibrations overpower the defect's funneling effect, instantly snapping the direct current and reversing its flow. Knowing exactly how this thermal reversal triggers gives researchers a reliable steering wheel to actively direct where the electrical current goes on demand. They mapped out the thresholds where the material's structural flaws yield to its thermal vibrations. By mastering these two chaotic variables, they established a predictable method to control ambient energy harvesting for commercial use. Understanding the mechanics of these tiny structural flaws allows engineers to pull this quantum phenomenon out of theoretical physics and begin designing real, self-powered devices. The immediate targets are low-power electronics. Think of medical sensors that monitor human vitals indefinitely using body heat, or wearable technology powered by the radio waves naturally bouncing around your living room. Looking at this schematic, you can see a possible macro-scale application. By integrating these topological nodes, telecommunications networks could eventually power their own core computing components by absorbing the same wireless signals they transmit. It is a striking irony. We have spent well over a century relying on volatile chemicals and striving for perfectly pure manufacturing conditions just to store temporary electrical charges. This breakthrough suggests that instead of fighting against material imperfections, we can design specifically for them to capture ambient energy at room temperature. If you want to understand the hidden physics and unexpected mechanisms controlling the future of our technology, make sure to subscribe to the channel. The next major leap in human capability may not come from larger batteries, but from finally mastering the invisible, chaotic forces that already surround us.